In the lesson today, we are going to discuss capacitors. The topic capacitors is under electric and magnetic fields, and you can see that it is chapter 7.2. We have three subtopics, 7.2.1, 2 and 3. I also have the notes here which I will be using during the lesson. I have also further classified the notes. As you can see over here, this is 7.2, and then we have three subtopics. So I have classified it as 7.2.1, 7.2.2, 7.2.3 in the notes. You can see it here, 7.2.1, 7.2.2 and 7.2.3. 7.2.1 is about the capacitor basics. 7.2.2 is about charging and discharging capacitors. In the case of charging and discharging capacitors, we have some graphs and equations of graphs. Let me show you those. And then we have the mathematics involving the capacitors. Now in capacitor basics, I will show you what the capacitor looks like and what it's made up of, how it works and things like that. So let's first have a look at the entire lesson briefly, so you can have an idea of what you're going to learn about. Now you see here chapter 7.2.1. Yeah, so here we have the capacitors, and here is a photo of the capacitors. Let me show you a better one. Now see, these are all capacitors here. This you see, the cylindrical shaped ones are the capacitors, and on the capacitor the capacitance is given. See over here, this is 4700 microfarads. So each capacitor has a capacitance. Then it also tells us the maximum voltage that you can connect across this. So for example, here it's 35 volts. Now for this it is 16 volts, and you can see the bigger the capacitor, the greater would be the capacitance and also the potential difference that it can have across it. And we also have the flat ones, the capacitor. So a capacitor is made up of two parallel plates. Now the parallel plates can be like this, you see over here, parallel to each other and flat, or they can be rolled, like in the case of a Swiss roll cake. You'd have 8 cakes like a Swiss roll. So here you have the two plates, one on top of the other, and they are rolled. Like imagine you have one carpet over another carpet, and then you roll the carpet. So this is also like that. So in the capacitor we have two plates, two metal plates, two conductors, and between them we have an insulator which is called a dielectric material. This dielectric material can be air, it can be mica, it's an insulating material. Now charge doesn't flow between the plates of the capacitor. If it flows, then it damages the capacitor. So remember, you saw the voltage that was mentioned here. Now if you connect a potential difference across this capacitor which is more than 35 volts, then even the dielectric material can start conducting, and then the charge will flow between the plates. So this will damage the capacitor. Now what is a capacitor, by the way? Capacitors are used to store energy in electrical and electronic circuits. So first you can have an idea of what capacitor looks like. We have the cylindrical shaped capacitors and the flat ones. Capacitors are used to store charge. Now we will see how the charges are stored. And by the way, this is the equation for a capacitor. Q is equal to CV. Q you have already learned is the charge. C is the capacitance. Over here you saw the capacitances labeled on this capacitor. See, 4700 microfarad is the capacitance of this capacitor. 100 microfarad is the capacitance of this capacitor. And you can see here, this is 16 volts. Then we have so many other capacitors here. See, this is 35 volts, 470 microfarads. And here you can see 4.7 microfarads. I think it's 35 volts. And then we have the flat ones. Okay. Alright, so here is the first slide. This is chapter 7.2.1 capacitor basics. So you should know this equation. Q is the charge on one plate of the capacitor. Remember, the capacitor has two plates. So we consider the charge stored on one plate of the capacitor. C is the capacitance of the capacitor. V is the potential difference across the capacitor. So in other words, we can say that C, the capacitance, is the charge to potential difference ratio. So you see here the capacitance of a capacitor is the charge stored on one plate. Remember, it's not on both plates, it's the charge stored on one plate per unit of potential difference between the plates. V is the potential difference across the plates. This is the symbol for a capacitor. We have two parallel lines to indicate a capacitor. In the case of a cell, we had two lines. One was longer than the other one. But in the case of capacitor, both lines are of equal length. So here we have capacitance of the capacitor. V is the potential difference across the plates, and Q is the charge stored on one plate. Here you have a diagram of a capacitor, and here is another diagram. The construction of two types of capacitors. Now, in the case of the cylindrical capacitor, the dielectric substance again is between the metal plates. Okay, so we have the metal plates. Always between the metal plates you have the dielectric material. It can be mica, it can be air, which is the dielectric material. Then also we have the other equations for capacitance. Let's first go through the other slides also. So you saw the diagrams, the photo of the capacitors. And by the way, if you are taking at this stage, you don't need to know in so much detail, but there can be some practical lessons that you would have done in unit practical example. So if you have gone through them, you might learn that this is the negative terminal of the capacitor. You can see a negative sign here. You see here. So you connect this side to the negative terminal of the battery. So here you see here. Okay. Now this is the diagram explaining charging and discharging capacitors. Now when you charge a capacitor, this is the symbol for the capacitor, this is the symbol for a cell. We have a resistor here. Always when we connect the capacitor, we connect it through a resistor, because this will not allow a very large current to flow through the capacitor. Because if a very large current flows into the capacitor, actually not through, it flows into the capacitor can get damaged. So we want the current to go through the capacitor increasing gradually or decreasing gradually. That's why we use a resistor. And similarly, when we discharge the capacitor also, we discharge through a resistor. Now in this case, we don't need to draw two resistors here. We can simply have only this resistor. We don't need to have another one here, so that when it's charging and also when it is discharging, the current flows through only that single resistor always. Okay, so here you can see the switch is connected so that the capacitor, resistor and the cell are connected in series, and this will charge the capacitor. But here you see the cell is not connected with the capacitor, so here the charge stored on the capacitor will discharge through this circuit. So we will see the details afterwards. And here we have a Greek letter tau. This is called the time constant. It is R, the resistance of the resistor, times the capacitance of the capacitor. These are the diagrams for capacitors charging and discharging. You see here 7.2.2 capacitor charging curves and equations. Then for capacitor discharging 7.2.2, again capacitor discharge curves. So here this is discharging, and you have to be familiar with these calculations. And also here I am showing you some unit analysis. We have this time constant tau, which is equal to R times C, the resistance of the resistor through which the capacitor discharges, times the capacitance of the capacitor. Now T is the time constant, it has the unit seconds, R has the unit ohms, C has the unit farad, F, capital F. So again, capacitor discharging, these are the equations. You have to be familiar with them. You should know how to use them, do calculations using them. And we will go into more details about this time constant. In brief, the time constant indicates how long it takes for the current to decrease to 37% of the initial value. If you are taking mathematics, you would have learned about exponential decay and exponential growth curves. So if it's an exponential decay, we have power with a negative sign here. So this indicates that the shape of the graph will be like this. It's an exponential decay curve. Similarly, you can see here again minus sign here, minus sign here. So this is for capacitors discharging. Now if you go back to the slide about capacitor discharging, you can see all of them are exponential decay curves. So if you look at the three equations for capacitor discharging, that is in terms of charge, in terms of voltage, in terms of current, all have exponential decays, and the negative sign here indicates the shape of the graph. In this case, because the power is negative, it will be an exponential decay curve, which means it will be this shape. We will go into the details later. So we have capacitor discharge curves, and also we have capacitors charging. Now if it is charging, you can see we have only one thing that is different, that is this, but all the other curves are like this. See, only this one is this shape. So this is the current versus time, and you can see the equation is like this, but for these two, these are the equations. So there you have a 1 minus. Alright, let's go back to the beginning, and now we will learn this in detail. Alright, so here is the first slide. Now let's also have a look at this from your textbook. So let's go to chapter 7.2, which is on page 48. Okay, so you see here capacitors, capacitor basics, this equation, and there are some calculations involving this equation. So remember, capacitance can be calculated by the equation. Capacitance has the unit farad, capital F, is equal to charge stored on one plate of the capacitor divided by the potential difference across the capacitor, means across the plates of the capacitor. This is the equation in symbols. C is the capacitance, equals Q over V. Now remember, C is for capacitance. Don't confuse it with charge. We use the letter capital Q for charge. You might think C charge also starts with C, and then you might get think, okay, C is the charge. So don't make that mistake. Sometimes students may confuse that. So remember, C is for capacitance, Q is for charge. When you learn the equation for current, Q is equal to IT, there also you had Q. Q was the letter that we used for charge. Let's go through this example. What is the capacitance of a capacitor which can store 18 millicoulombs of charge when the potential difference across it is 6 volts? So very simple. You are supposed to find the capacitance C, and you know C is equal to Q over V. Q is given, that is 18 millicoulombs. Milli is a metric prefix, and it has the numerical value 10 to the power minus 3. So we can replace the M with its numerical value 10 to the power minus 3 and substitute it here. So 18 millicoulombs is equal to 18 times 10 to the power minus 3 coulombs, and the potential difference across the plates is 6 volts. So substitute that, then we get 3 into 10 to the power minus 3 farad. So if you convert it to microfarad, it will be 3 microfarads. Okay, so you see again, if you read the question, what is the capacitance of a capacitor which can store 18 millicoulombs of charge? So remember, this is referring to the charge on one plate of the capacitor. What happens is, the charge initially is the same on both plates. It's actually neutral. Okay, so it's neutral, and when you connect it to a cell or a battery, the capacitor gets charged. So we will see the details also. How much charge will be stored on this capacitor if the voltage is increased to 20 volts? So now we are supposed to find the charge Q. The capacitance is a constant for that capacitor. You saw the photos already. It's a fixed value for a certain capacitor, that is the capacitance. Okay, so for example, like if you consider a resistor has a fixed resistance. If you see a fixed resistor, it has a fixed resistance. Similarly, a certain capacitor has a fixed capacitance. Now keep in mind, don't confuse that voltage which is labeled on the capacitor to be the voltage across the capacitor. This is the maximum voltage that the capacitor can bear. If you connect something more than 35 volts, if you connect a cell, a battery that has that will cause a potential difference across this more than 35 volts, then what will happen? Then the dielectric material can't provide the resistance. So then current will flow through the capacitor and damage the capacitor. So that is that is the maximum potential difference across the capacitor. Now if you look over here, it is increased to 20 volts. They don't mention what the maximum potential difference that the capacitor can bear, so we just ignore that and we go with this. Okay, so Q is equal to CV. How much charge will be stored on this capacitor if the voltage is increased to 20 volts? Q is equal to CV. C is the same because it's the same capacitor. We found it previously, 3 millifarad. Milli is 10 to the power minus 3. V is 20 volts. So we get 0.06 coulombs. This is the charge that can be stored on this capacitor if the potential difference connected across it is 20 volts. Okay, so in the third example here we are using the other equation. So before we go to that, let's have a look at the notes. So you saw the photo, now here is the notes. Okay, so what is a capacitor? Capacitors are used to store energy in electrical and electronic circuits. We can also say it stores charge. So when it stores charge, it stores energy. This is the main equation, the first equation. Q is equal to CV. I already explained it briefly. Now see, I use the square bracket here to indicate that the capacitance for a certain capacitor is constant. The square bracket indicates it's constant. Units, already I explained. So these are the symbols of the units, and this is the units in words. Coulomb equals farad times volt. Here we have a graph. V equals Q. Now you know that C is a constant. So if you plot a graph of V versus Q, you should get a straight line passing through the origin because C is a constant. So you see, if I rearrange this equation so that I have V equals 1 over C times Q. Okay, I have shown the working here. So we have Q is equal to CV. Then if I make V the subject of the equation, I have V is equal to 1 over C times Q. Capacitance is a constant, so the 1 over C will also be a constant. That is, the reciprocal of the capacitance will also be a constant. So if you plot a graph of V versus Q, that means V on the y-axis, Q on the x-axis, the gradient will be 1 over C. So gradient is equal to 1 over C. So that is also the change in V divided by the change in Q, 1 over C. So this is the graph that we get. Now you remember, it's similar to the graph of a spring that obeys Hooke's law. F is equal to Kx was the equation there. So remember that. So when you plotted that, you had some shape like this, and remember we said that the area under that graph is the energy stored in the spring or the work done on the spring. Similarly, over here we can say that the work done on the capacitor, that is, or the energy stored in the capacitor, is equal to the area under this graph. So W or E is equal to half QV. The area under this graph is the area of a triangle. Area of a triangle is half into base into height. So half into Q into V. Now for this we can also substitute using this equation. So if I substitute for Q CV, okay, from this equation Q equals CV, if you substitute CV for Q, you get CV times V, which is CV squared. So here we have another second equation. Now this second equation doesn't have Q, but it has the other two terms, other two parameters, C and V. The first one doesn't have C. Okay, then the last equation here, if you substitute for V, see, V is equal to Q over C. So we get Q squared over C. So this is what you get. By the way, the definition of capacitance is very important. In the exam paper, they can ask you to write down what the definition is. So here is the definition. The capacitance of a capacitor is the charge stored on one plate per unit of potential difference between the plates. So make sure you memorize this with understanding, because in the exam, if they ask you to write the definition, and if you miss certain keywords you might not get the full mark. So that's why I ask students to memorize with understanding. So remember, charge stored on one plate per unit of potential difference between the plates. Now when you practice the exam papers where you write these kinds of definitions, and when you check the mark schemes you will be familiar with what keywords that they are looking for in the answer. Okay, so you know work done equals energy transferred, so the work done on a capacitor to charge it is equal to the energy stored or gained by that capacitor. So the more charges that flow to the one plate of the capacitor, the more energy it stores. The capacitance C of a capacitor is defined by capacitance is equal to charge divided by potential difference, or C is equal to Q over V, where Q is the magnitude of the charge on each of the capacitor's plates and V is the potential difference across it, that is the capacitance. So Q is the magnitude of charge on each of the capacitor's plate. So you can take one. Okay, so each one means either the positively charged plate or the negatively charged plate, and V is the potential difference across the capacitor, across it, which is the capacitor. So you have a variety of capacitors here. Now how does the capacitor get charged? I don't think we discussed that yet, so let's see. Now this is the symbol for a capacitor. Two lines of equal length are here, so you can compare this with the symbol for a cell. Now symbol for cell has one long line and one short line. Here both lines are of equal length. Actually I think to avoid any confusion I should have removed this resistor from here. Okay, so imagine this resistor is not here, because otherwise you might confuse it with the R here, because when you have this R here, for example when it is discharging, then it will be the total resistance along this branch. So it will be the resistance of this plus the resistance of this when it is discharging. But if we don't have this, then it's only the resistance of this, which is R. Okay, I have labeled R here, so yeah, better to remove this. Okay, let's see, we can refine the notes afterwards, but now I have told you. Okay, so here is capacitor charging. Now first, before we charge the capacitor, we can first completely discharge it. How we discharge it is, we can connect the terminals of the capacitor like this through a resistor. So what will happen, any extra charge will flow through and go to the other side, so that it becomes neutral. What do we mean by extra charge? When a capacitor is charged, there will be more charge on one plate compared to the other plate, meaning more negative. Now for example here we are charging the capacitor, so what will happen is, when you connect this initially, let's say this capacitor was neutral in the beginning. Okay, so no additional charge on one plate compared to the other plate, so it was neutral. Now what happens is, when you connect this to a cell or a battery, this is the positive terminal of the battery, this is the negative terminal. So what will happen is, the battery is an electron pump, it pushes the electrons around the circuit. Okay, but remember, charge doesn't flow through the plates of the capacitor. When we connect a power supply which has a EMF less than what is marked on the capacitor, then it will not be a potential difference more than what the capacitor can bear. So what will happen is, we connect this. Now in the beginning the capacitor was neutral, the charge will then be pushed. So what will happen, this is the negative terminal, the charges will be pushed around this. So what will happen, the electrons that are here will be drawn towards the positive plates. Why? Because positive and negative attract. So since positive and negative attract, let me draw this here also and show you. So here we have the symbol for a capacitor, then we don't directly connect it to a battery, because then there can be a large current flow, and then it can damage the capacitor. Okay, so let's say this is what we have. So this is, let's say, 6 volts. Now this is initially uncharged. Okay, so now what will happen is, the electrons will be drawn towards the positive plate from this side, because here we have a positively charged plate, electrons are negatively charged. So then what will happen, they will be drawn this way. electrons will flow like this, and over here we have negative charge, so the electrons will be pushed this way. So what will happen is the electrons will go from here all the way to here, and they will accumulate here until the potential difference across the capacitor equals that of the cell. So until it becomes 6 volts, this will continue. But in the beginning the charges will flow at a faster rate than later on. So why is that? The reason is, in the beginning, remember, there was no net charge here, so they can easily go over here. But what happens with time is, the more negative charges that accumulate here, the more the repulsion will be to the incoming negative charges. So so let's say one negative charge goes from here to here, okay, then the next negative charge is coming. Now when the next one is coming, there will be some repulsion from the already negative charge that is here, okay. So then the second one went. So when the second electron goes here, then there will be a net positive charge there. So first one went, you have one positive charge. Second electron went, you have another positive charge, net positive charge. Here you have two net negatives. Now let's say the third electron is going like this. So what will happen? Now it will leave another net positive charge here. So the electron goes here, so net negative. So that process continues until the potential difference across the capacitor is equal to the potential difference across the battery, okay, or we can say the terminal potential difference across the battery. And if it doesn't have internal resistance, we say that the EMF of the battery is equal to the potential difference across the capacitor. All right, so this is what happens. Now remember, for every electron that goes there will be more and more repulsion from the for the next electron, because there are more and more negative charges here to cause more repulsion. And also when this becomes more positive, there will be more attraction from this side for the electron that is going away. So in the beginning, when the first electron went, we can say there is no attraction from this side, or as it goes there will be a positive, so there will be little attraction here, no negative, so it will go there. Then when the second electron is going, then there are two positive charges created here, so there will be some attraction from two positive charges. Then when it is going, when it is here, there will be repulsion from one negative charge, okay. So then let's say the second electron comes here, then the third one is going. So when the third one is going, what happens? There will be attraction trying to prevent it, or to prevent it going by attraction from three positive charges. So but it still goes because the battery is the electron pump. Then what happens when it is going? Now already there are two negative charges, so earlier the repulsion was from one electron, now there is repulsion from two. So you see, the more it gets charged, the slower it gets charged, the lesser and lesser will be the flow of current this way. So the electrons are flowing like this, but they don't go through this, because here we have the dielectric material. Remember, the word is dielectric material, which is an insulator. So the charge doesn't flow through this. So the charges go like this, they accumulate here. So this gets positively charged, this plate, and this plate gets negatively charged until the capacitor becomes fully charged, depending on the potential difference, or EMF, or terminal potential difference of the cell. So that's how a capacitor is getting charged. Now we will also see how the capacitor gets discharged. So now remember, we charged this capacitor, then we move the switch to this side. So earlier you see the current is flowing only here. Remember, for current to flow there has to be a complete circuit. Current can't flow here because there is no complete circuit here, there is a gap here. So the current is flowing like this, but remember again, it doesn't flow through this gap. The current flows like this, and then it charges the capacitor. Now we have the fully charged capacitor with a potential difference across it of 6 volts, okay. Now we connect it this way, we move the switch to this side. Earlier the switch was here, now we move the switch to this side. So now the second circuit is complete. This second circuit doesn't have a battery, but it has the capacitor, and then we have the resistors, okay. So what will happen? Those accumulated electrons will now flow this way. This is the direction of flow of electrons. The electrons will flow this way until it gets completely, until the capacitor gets completely discharged, as long as we have the connection until it gets completely discharged. So let's see that also. I'll use a different color. Now in the second circuit, remember this capacitor is 6, now it's charged to a potential difference of 6 volts, and it's connected, remember that resistor is still there. Okay, so now it's connected like this. So again, remember, we connect it through a resistor so that there won't be a sudden large current flow which can damage the capacitor. Okay, so here what happened in this charging phase, the potential difference of the capacitor went from 0 volts to 6 volts, where it got fully charged. 0 volts to 6 volts. Now over here, this capacitor is getting discharged. So here it is discharging. So when it is discharging, the electrons will flow. Remember, the electrons were accumulated here, so they will go this way, in this direction, until they go back and neutralize the positive charge here. Okay, so you have an equal number of positive charges and an equal number of negative charges when it is charged. When it becomes neutralized, the charge will be 0 on both plates. So no net charge. Okay, 0 volts, 0 charge here. No positive charges, in other words, no negative charges when it has fully discharged. Okay, so the E stands for electron. Electrons will flow like this, and again, what happens in the beginning, there will be a large current, the highest current, and then it will decrease with time. Why? Same as before. Here what happened, in the beginning you have the highest current, and with time the current decreases because there is repulsion. Now over here also similar thing happens. Here there is attraction. Okay, so what happens, the negative charge that is coming is attracted here by 4 positive charges. Okay, so it comes. Then the second electron that is coming, now remember, the first electron went and it neutralized 1 charge. So when the second electron is going, it has attraction only from 3 positive charges. First one had attraction from 4 and repulsion from 3. So it will go fast compared to the second one, which is a bit slower. So the second electron has attraction from 3 positive charges and repulsion from 2. Then the third electron that is going here, remember already 2 are neutralized, so it will have attraction only by 2 positive charges and repulsion by 1 negative charge. So what happens is, with time the current will decrease. So this will help us understand the graph that we have. Okay, so here also you have a graph. If you draw a graph of current versus time, so in the beginning you have a high current, and then it will decrease, and eventually the current will be 0. Same thing here. Here also, in the beginning you have a high current. I mean, in the beginning means at the very beginning the current is the highest, then it will decrease with time. Okay, so what happens, again it will decrease, and eventually when the capacitor is fully charged, there won't be any flow of charges, so over here, and when it is fully discharged, then that means it goes from 6 volts to 0 volts. So when 0 volts, there will be no flow of charge. Remember, for charge to flow, there has to be a potential difference. Charges flow, positive charges. Okay, the current flows from high potential to low potential. So over here you can see the direction of flow of current is opposite to the direction of flow of electron. So electron flow is this way, that means the current flow is the other way. See, from low potential minus to plus to high potential. Over here the electron flow is this way, that means the current flow is the other way. Always the direction of flow of current is opposite to the direction of flow of electrons. Remember, the positive charges never move because they are effectively locked in the nucleus. You get the positive charges in the nucleus. Why? Because those are the protons. In the case of flow of current, electricity, it's always the electrons that are moving. Electrons are negatively charged. Okay, so remember, the positive charges don't move. it's the negative charges, in other words the electrons, that move. Okay, so when it is discharging also, what do we have? We have the current decreasing, like in an, yeah, it will decrease like that. Okay, eventually it will become zero when the potential difference across the capacitor becomes zero. Okay, so this is why the graphs for current in both cases, in the case of charging and in the case of discharging, is like this. But the other graphs will not be the same. So I showed you in the beginning. Okay, so now I think you understand this. First let's have a look at the graphs again. See here, capacitor charging, you see the current decreases with time. Then capacitor discharging also, you can see it will be, yeah, so here capacitor discharging, current is decreasing. See, capacitor charging, current is decreasing. But the others, see, when the capacitor is charging, potential difference will increase and it becomes a fixed value. Why? Because you see, in the beginning when the capacitor was charging, the potential difference was zero. It was completely discharged, the capacitor, in the beginning before it was connected. So when it, at the moment you connect it, that is when the time is zero, the potential difference across the capacitor is zero. Then we increase it to, it increases to 6 volts. So from 0 to 6, the potential difference increases when the capacitor is charging. See, from 0 to 6 it increases. Now again you can see this curve gradient is decreasing. Here also the gradient is decreasing. If you want to find the gradient of a curve, you can draw the tangent to that curve. Gradient is also called the slope. So if you draw tangents along these curves at different points, you can see that along the curve, the gradient of that tangent, or the slope, also called the slope, gradient is also called slope, slope decreases with time. Same thing here. See, the slope, the rate at which the potential difference increases, the gradient decreases with time, and eventually it becomes 6 volts. When it is charging, it reaches the maximum value, which is the EMF, or terminal potential difference, okay, across the cell that is charging it. Okay, remember there is a difference between terminal potential difference and EMF. Okay, so if we assume there is no internal resistance in the cell, then we can say the terminal potential difference is equal to the EMF. Now in these cases we can assume its internal resistance is 0 and do these calculations. Okay, now over here, what about charge? So charge also, in the beginning there was no net charge, right? And with time what happens? The charge becomes a maximum value, but you can see the rate decreases. Why? Because there is repulsion. So that's why the gradient decreases with time. Here also, if you draw tangents along this curve at different points, you can see the slope of the tangent decreases. Here you have the maximum slope, here the slope is 0, here slope is 0. Okay, so the gradient decreases with time in all cases. The rate decreases with time because there is repulsion from the charges that are already present for the incoming charges when the capacitor is charging. When the capacitor is discharging, you can see again the slope is, the gradient is decreasing with time. Okay, when the capacitor is discharging, remember these three are for discharging capacitors. The potential difference across the capacitor was initially 6 volts because it was fully charged, and then it dropped to 0 volts. See, it drops to 0 eventually. Okay, now why is the gradient of this curve decreasing with time? Because again, remember, there is repulsion, or there is, in other words, there is less charges to cause attraction and repulsion. Okay, so from this side there is less repulsion, from this side there is less attraction, because the more charges that flow to that side, the more will be the neutralization of those charges, and less charges to cause attraction. Okay, so we can say the same thing applies for this also. Charge on capacitor, with time the flow of charge becomes lesser and lesser, so the charge on the capacitor decreases, but at a again a decreasing rate. Okay, so I think that helps you to understand how the capacitors are getting charged and discharged. And we also have these equations for capacitors charging and for capacitors discharging. I have given the, yeah, see, this is for capacitors discharging. Now you have to be able to use these equations and do calculations. Okay. All right, so let's go back to the first slide. Remember, over there we had the equations here, and in your textbook there was an example. So let's go through this. What is the energy stored on a charged 100 microfarad capacitor which has a 3 millicoulombs of charge? So very simple. E is equal to, we can use this equation. Why? Because we are given the charge stored and the capacitance. So this is the amount of charge stored on a plate of the capacitor, and this is the capacitance of the capacitor, 100 microfarad. So based on this, we have been given the charge, we have been given the capacitance, so we are going to use this equation here. W is equal to Q squared over 2C. So let's substitute that. Q is 3 into 10 to the power minus 3. Remember to square that. Then we have the half. Then capacitance is 100 microfarad. Micro is 10 to the power minus 6. So substitute and you get the answer in joules, because you substituted everything here in SI units without any metric prefixes. So this is the energy stored on the capacitor. Or we can say this was the energy of supplied, or the work done on the capacitor, assuming there are no losses. Okay, so now we did an example using this. So this slide is now complete. Okay, I think you understand everything in this. So let's go to the next one. I think I explained this. Now charging and discharging capacitors, I explained this, but what about this? Q is equal to CV. Okay, one more thing. Now if you have a fixed potential difference across a capacitor, the amount of charge that capacitor can store, the square bracket indicates the potential difference. Let's say is a certain, we have a battery, let's say like this, 6 volts, but the greater the capacitance of the capacitor, the more charge it can store. Okay, so for the same potential difference, if the capacitance is higher of that capacitor, it can store more charge. So remember, Q equals CV. So for a certain potential difference, the greater the capacitance of the capacitor, the more charge it can store. Then we have this tau equals R over C. The T is the time constant. You can say this is tau, you can say this is T. Okay, so T is equal to RC. Again, this is a Greek letter. If you are not familiar with the letters of the Greek alphabet, you can go through the lesson on the Greek alphabet that I have created. You will understand the Greek letters, because we use a lot of Greek letters in physics and also in mathematics. So it's better if you are familiar with the Greek alphabet. Okay, so capacitor charging curves. By considering the charging process in the same way as we did the discharge of capacitor in figure A, so that was over here. Okay, so I already drew this diagram and explained it to you, but let me show it to you from the book. Okay, so now we are in chapter 7.2.2. we have already completed 7.2.1. okay, capacitor basics. See, electrons move from the positive to the negative. This is the symbol for a capacitor. The letter is capital C, which is used to indicate the capacitance, but the unit of capacitance has the letter capital F. So don't confuse the C for charge and the C for capacitance. Okay, and then we learned about energy stored in capacitor. So make sure you answer all these questions and check the answers from the answers to this textbook. Okay, so make sure that will ensure that you have understood the relevant material. Also, you can go through the revision, the notes, and understand it. Then the key definitions are very important. A capacitor is an electrical circuit component that stores charge and so can be used as an energy store. So we can say it stores charge, it stores energy, it stores charge, so therefore it stores energy. So it will have the potential to do work by letting the charges flow through it when we are discharging the capacitor. Capacitance is a measure of the capability of a capacitor, the amount of charge stored per unit voltage across the capacitor. It is measured in farads. Capital F is the symbol for capacitance, farad. Okay, so this is the diagram. I think I also have it in the notes over here. Yes, see figure A, investigating current flow through a capacitor. So I already explained this. See, 100 microfarad capacitor, 6 volt. then we have a bulb here. Now what will happens is when we connect it like this already has a resistance. Okay, so this is all, since this component has a resistance, so it's like a resistor that is connected with this circuit. So we connect this. Now it will charge the capacitor to 6 volts, and when you connect the switch here, what will happen? The capacitor will discharge through the bulb. So in the beginning the bulb will have the maximum brightness, and with time the brightness of the bulb will decrease. If you have a resistor with a very high resistance, it will take a longer time for the bulb to turn off, because the greater the resistance, the longer it will take to discharge, and also it will take a longer time to charge. So the lesser the resistance, the quickly it will discharge and it will charge. Okay, so over here, for example, if you have a resistor with a very high resistance, it will take a long time for the capacitor to charge. Same way, when you connect it to discharge, if the resistance is high, it will take a long time to discharge. If the resistance is low, it will take less time to charge and also less time to discharge. Remember, this R is an external resistor. It's not the resistance of the capacitor. Okay, don't confuse. R is a resistor that is outside the capacitor. It's not the resistance of the capacitor. Okay, so let's go through this. Investigating how the current through a capacitor changes over time. You can investigate. Now in unit 6 you may have questions like this. Unit 6 paper, you can investigate how the current through a capacitor changes over time by connecting a data logger which senses current in series with the capacitor and then charge and discharge it. A suitable setup for this is shown in figure A. This setup could be altered to log the potential difference across the capacitor over time. So you see this diagram, we can get these graphs from this. Okay, the current sensor, computer, data logging current. So it's connected to a computer and it can give us a graph of how potential difference varies with time, how charge varies with time, how current varies with time for the capacitor charging and also for the capacitor discharging. A suitable setup for this is shown in figure A. This setup could be altered to log the potential difference across the capacitor over time. Using a voltage sensor in parallel across the capacitor, make sure you have a good understanding of this practical, as your understanding of the experimental method may be assessed in your examination. So that's what I told you in the unit 6 paper, whatever is in this textbook under investigation, okay, work problem like this can be tested in your unit 6 practical exam papers. So I have also included this in the notes here, but the text appears a bit small, we have to zoom in, so because of convenience I used this. Okay, so you have these graphs, very important. Now you know why the shapes are like this, why this is the same for both the charging and discharging, but for charging the graph is like this for potential difference and for charge. Why? Because with time, when the capacity is charging, the voltage increases, the charge on the plate increases when the capacity is charging, but when the capacitor is discharging, the potential difference across the capacitor decreases, the charge on the plate of a capacitor decreases. Okay, so here we have these equations, be familiar with them because you may have to use them. And remember, because this is increasing, we have this 1 minus term here, but for discharging we don't have that 1 minus thing. Okay, so if you look over here, discharging, capacitor discharging, you don't have that. See, it's like this. Okay, so capacitor discharge, capacitor charging. Okay, let's see. By considering the charging process in the same way as we did in the discharge of capacitor in figure A, we can quickly work out that the charging process produces graphs such as those in figure D. Charging curves for a capacitor connected to a 6 volt supply. So remember that maximum voltage will be the voltage or the EMF or the terminal potential difference of the battery or cell that is connected to charge the capacitor. Okay, so based on this and based on the equation Q equals CV, we can figure out this value and these other values. Okay, so charging current, from the initial current we can get that, and there is a way we can calculate the initial current, because in the beginning we have only that resistor, this resistor and this, so we can find the current because V equals IR. So you know V, you know R, so you can find the initial current. Okay, with the calculations you will understand this. So there is some mathematics also involved in this. So let's see. Okay, so that is for capacitors charging. You have the equations for charging, you have the graphs for capacitors charging. Charging curves for a capacitor connected to a 6 volt supply, and we will figure out how we can get these numbers here. Like I said, you can get it from the V equals IR, because in the beginning you know that the capacitor is discharged. So the potential difference, okay, one more thing, in the very beginning when the time is 0, the potential difference across the capacitor is 0. The potential difference across the resistor will be 6 volts. Then what happens with time, when this is getting charged, the potential difference across the resistor becomes 0 or decreases to 0. The potential difference across the capacitor increases to 6 volts. So if I want, I can also do it here, draw it here. So over here, remember, the potential difference across the capacitor increased from 0 volts to 6 volts. But at the same time, the potential difference across the fixed resistor decreased from 6 volts to 0 volts. So when the capacitor is fully charged, there is no current flow, so the potential difference across this is 0. So in the beginning, the potential difference across this was 6 volts and it dropped to 0 volts. Okay. Also, you know the Kirchhoff's laws. So remember, across this branch, the potential difference should be equal to the EMF across this, okay, because it's this. So you can understand it that way also. Now, yes, so I have explained all this. So again, we have this time constant. Remember that time, the longer it takes to charge or discharge, the greater the resistance of the external resistor. Alright, so we went through this. So again, first have a good look at what the axes are. Always whenever you get a graph, you should have a look at what the axes are. Here, charging current versus time, potential difference across capacitor versus time, charge on capacitor in millicoulombs versus time. Alright, so let's do the calculations over here. Now remember this, you can imagine that the capacitor is discharging, okay, so it's connected here. So this we can assume the resistance is negligible, and you have to remember it's connected this way. The capacitor is discharging now, okay, this diagram here, okay, there is a resistor. This you can imagine this resistance is 100 ohms. It's labeled here, see, 100 ohms. Now to find the initial current, that is at the very beginning, when the capacitor begins to discharge, that current I naught, actually, okay, I should have included a 0 there. I naught can be found using V equals IR. So V, remember, the potential difference across the capacitor here when it is fully charged is equal to what? 6 volts. So here you can see 6 volts, and it's discharging through a resistor of 100 ohms. So in the very beginning, when the capacitor is fully charged, it has a potential difference of 6 volts and the resistance here is 100 ohms. And what happens then? The 6 volts drops to 0 volts. So we are using the 6 volts to find the initial current I naught. Using this we can do that. So V is 6 volts, I is I naught, R is 100 ohms, okay, when the capacitor is discharging. So we get 0.06 amperes. So that's why this here is 0.06 amperes. See, in the note you can see that 0.06 amperes here, because that is the initial current. Then what happens? Eventually it drops to 0. 0 is when the capacitor is discharged. Alright, so let's see how we can get these other values also. Now over here, let's see, we can find the capacitance of the capacitor. And by the way, you know this is 6 volts because the capacitor was fully charged. So when the time is 0, it starts from 6 volts. Okay, so Q is equal to CV. Capacitance, you can see it's given here, 100 microfarads. 100 microfarad. Okay, so with this we can also find the charge here. Okay, I have done it the other way here, but if you use the equation Q is equal to CV, Q we know is 0.0 okay, so let's follow this. Okay, so this is the capacitance. Okay, so what we are going to do is we are going to find the initial charge or the maximum charge that the capacitor will have when it is fully charged, meaning just before it gets discharged or after it is fully charged. You can see that the charge is 0.6 millicoulomb. So let's see how we got that. Now remember, if you consider this, the resistance is 100 ohms, so I have labeled that here 100 ohms. The capacitance of the capacitor is 100 microfarads. The initial charge on the capacitor is 6 volts. So let's use Q is equal to CV to find the initial charge. Now initially the potential difference across the capacitor is 6 volts. The capacitance of the capacitor is 100 microfarad, which is 100 into 10 to the power minus 6 farads. Then when we multiply this, we get 600 microcoulombs. So this is the initial charge. As soon as when the time is 0, when it begins to discharge, this is the maximum charge it has. So we can convert this to coulombs. It's 0.0006 coulombs, and if you convert it to microcoulombs, it will be 0.6 microcoulombs. So you see the initial charge is 0.6 microcoulombs, and that is what is shown over here. See, 0.6 microcoulomb. So now you learned how to find the initial current, how to find the initial charge on the capacitor, that is the charge on one plate of the capacitor, and also you learned how to find the potential difference across the capacitor. The initial potential difference is 6 volts because that's the potential difference or the EMF of the cell. So it was charged to fully charged, so that's why initially when it gets discharged, when the time is 0, when it's discharging, this is 6.0 volts. So now you understand how to find this and also this. By the way, the working I have done here is the other way. So I use Q is equal to CV. I use this value here. Initial charge is 0.6 microcoulombs. Then I showed that the capacitance of this capacitor is 100 microfarad. So let's go through that also. See, I find this 0.1 microfarad. So here it's given in 0.1 millifarad. I have to convert it to microfarad so that I can compare that. So let's see. Actually what I have done is again the other way. I have used 100 microfarad and converted it to millifarad. Okay, so there is more than one way to do this. I have shown you all the different ways here, so finding with this also, but I think it's easier if you go through this first. Okay, so 100 micro. By the way, learning this will also help you to convert between units. So let's go through this. Now look at the way I'm going to convert this. 100 microfarad. Micro is a metric prefix which has a numerical value of 10 to the power minus 6. So I can replace or substitute for micro 10 to the power minus 6. The sign between the letters and the numbers or between the letters is a multiplication sign. So here it's a multiplication sign, here it's a multiplication sign as well, here as well as here. So I simply substitute the value. Then 10 to the power minus 6, I can also write it as 10 to the power minus 3 times 10 to the power minus 3. Because of the rules of indices, when you multiply, you add the powers if the bases are the same. So minus 3 is minus 6. So we have this 10 to the power minus 3. You know the metric prefix that has the value equal to that is micro. So then we have 100 into 10 to the power minus 3 is millifarad. Then this is what? 0.1. So 0.1 millifarad is equal to 100 microfarads. Again, if this is confusing, you can go through it, but what I wanted to show you is how to get this and this here, and I showed you in this slide the way to get this. Okay, so now you understand all these calculations. We went through this also from the textbook because the text there is a bit large, otherwise you will have to zoom in. So you have access to these notes. What is, okay, like a worked example, what is the time constant for the capacitor in the circuit shown in figure A? Let's go through it from the textbook because the text here is a bit larger. So time constant is tau, or some textbooks also write the letter capital T. T is equal to RC. So here it's tau, Greek letter, but if you look at the capital tau, it's identical to the letter T. So that's why people say T there. So T equals RC or tau equals RC. So if you look at the capital letter of this, it will be the same shape as a capital T. Okay, R is the resistance of this external resistor, and that is 100 ohms. Okay, so the capacitor is discharging through that 100 ohm resistor. Now remember, this is a lamp, but the lamp has a resistance, a bulb has a resistance, so we are going to use that. So it's like the resistor here, okay, 100 ohms. Then the capacitance of the capacitor is 100 microfarad. 100 microfarad. See, 100 microfarad. So let's use that and find the time constant. So we get 0.01 seconds. 0.01 seconds. Okay, 0.01 seconds. Okay, it's over here. Thus, in reality, the light bulb shown in figure A might flash on and off so quickly that we could not spot it, because this is a very short time. So when you discharge the capacitor through that lamp, you may not be able to see that the lamp is on, turns on and then it goes off, because it happens very quickly in such a short time. Okay, so that's the end of that. Now also here I have a unit analysis, and by the way, these are the equations that we have for capacitors discharging. Okay, so we have this Q naught is the initial charge. Now in the graph, that is the Q naught. If you go to this graph here, this is the Q naught. Then here we have the I naught, the initial current. Then here we have the V naught, the initial potential difference. So here Q naught, V naught, I naught. And then after a time t, if you want to find the current, maybe after 0.2 seconds, you can substitute 0.2, then you will get the current. Same thing here. If you know V naught, you can substitute the time, and then you can find the potential difference across the capacitor at that time t. Similarly, if you want to find the charge stored in the capacitor at a certain time t, you can substitute that, and then you can get. Now remember, R and C. R is the resistance of the external resistor that is connected through the in series with the capacitor when the capacitor is discharging. C is the capacitance of the capacitor. And by the way, the unit also I have shown here, and I think in the beginning I told you the time constant indicates how long it takes for the current to decrease to 37% of the initial value. So how is this 37%? Okay, so the example is here, the explanation is here. If we consider the charge at time tau, T equals TRC. So let's rearrange this. So we get this. Okay, so then we have, now look, if it's a bit confusing, you can okay, so imagine, okay, you multiply both sides by -1 RC, divide by multiply by -1. See, this is equal to this, so multiply both sides by -1 and divide both sides by RC. So then you get this. Okay, and then you can see this equation is already given here. So for T you can substitute RC. So then you get this. So when you substitute RC here, again, if this is confusing, just forget about this step and directly focus on this. Substitute RC when the time is equal to the time constant. Okay, so the time is equal to the time constant. So we substitute here RC. Okay, so then what will happen? This will become this 1. So this power is -1, and then what will happen? Here we have e to the power -1. Okay, so e to the power -1 is 0.37. Okay, so you see, then we get Q is equal to 0.37 Q naught, which is 0.37. You can also write it as 37/100, which is 37%. So the time constant tau is the time taken for the charge to become 37% of its original value. Okay, also we can say is the current, the time taken for the current to become 30. So for example, if you use this equation, if you substitute tau, or for T here, tau is equal to RC, then you can see it will be the same thing. Instead of Q and Q naught, it will be I and I naught and 37%. So I is equal to 37% of I naught. Okay, so that's how we get that. Now again, regarding the details, the mathematical part, it's all here. Now see, remember, this is 7.2.2 and 7.2.3, the capacitor mathematics. Okay, we'll also, now I have, I think, finished this slide. The explanation is complete for this. Okay, what about the units? I think you can work this out yourself. T is equal to RC. So we have second. I am actually showing you how the base units on both sides have to be equal and how they are equal, because in another example or exam paper question you might have something like this. So then you will have to break this down to base units and simplify and show that the second is equal to is the same on both sides. Okay, so here we have ohm and you have to go through this. So I have shown all the steps, step 1, step 2, step 3. So you can go through this and try to figure it out, and if you have any questions you can ask me. Now let's go through this last slide here, capacitor discharging. So whenever you get a graph, I told you first thing is you look at what the axes are. Here we have charge, here we have time. Now see, this is the initial charge, capacitor discharging. So when it's discharging, it starts with the maximum charge and then the charge gradually decreases. Now why we say the charge on one plate? Because if you consider both plates, they have an equal magnitude of charge, equal amount of charge, but opposite signs. So if you remember what I showed you in the beginning, see here we have 6 positive charges, here we have 4 positive charges, here we have 4 negative charges. So when one charge goes from here, it has to go here. So then the magnitude of charge on the plates is the same, but they have different signs. That's why we say in the equation Q equals CV, we say that Q is the charge on one plate of the capacitor. Alright, so we have these equations. Now I also show you over here what happens if you remember rules of logarithms. The power will become the opposite sign when it goes from numerator to denominator or denominator to numerator. So here it's in the numerator. So when we bring it down to the denominator, this power sign will become positive. You have learned this for rules of logarithms, I think, in mathematics. Okay, so let's go through this first. We have a curve. If we want to convert a curve to a straight line, we can use logarithm. So let's try. ln natural logarithm of q is equal to natural logarithm of q naught minus t over rc. See over here, actually it's showing you the other way. Applying the inverse function of natural logarithm gives this. Okay, so for example, if you apply logarithm to this by the rules of logarithms, I have a separate lesson explaining the mathematics required for physics, and under that I have the logarithms lesson. So you can go through that for more understanding, but now I will briefly tell you. So if you apply logarithm to this, then this will be logarithm. ln stands for natural logarithm. Okay, natural logarithm of q equals natural logarithm of q naught, this whole thing. Okay, so but since there is a multiplication sign here, then we can separate it like this. Natural logarithm of q naught plus e to the power minus t over rc. Now natural logarithm of e is 1. Okay, so then that power also can come down. So that's how we get this. Again, for more details, you can refer the lesson on logarithms. The details are explained there. Again, if you want more information, simply go online and search the rules of logarithms and you can see that's a complete lesson. Okay, I think you have learned this for IGCSE or O-level math. Okay, so logarithmic equations for voltage. But now again, for these kinds of questions, you can directly use this equation. Okay, this is the derivation. Logarithmic equations for voltage, we can take the log equation for charge and make substitutions to find equivalent equations for voltage and for current. So you see here, so we are applying this. Now for Q we can substitute CV. Then remember, this is the initial charge, so capacitance is fixed for a certain capacitor. Then V naught is the initial potential difference across the capacitor. Okay, so then we have multiplication. I told you, according to the rules of logarithms, when you have a multiplication, you can write it with a positive sign like this. Okay, you can separate them. Natural logarithm of C plus natural logarithm of V. Then same here, and we have this. Now you can see C is fixed, so natural logarithm of C is the same on both sides. We can cancel that out. Okay, so then we get natural logarithm of V is equal to natural logarithm of V naught minus T over RC. Now applying the inverse function of natural logarithm, again for details of this go through the logarithm lessons, but I showed you how you can get this from this. If you apply natural logarithm for this, then you will get this. So it's the reverse of that. Okay, so that's how we get this equation, this one here. So you also had this equation here. All right, so remember the the time constant. That definition is very important. Tau, time constant, is for a capacitor resistor circuit like this. Capacitor resistor circuit. Remember, R is the resistance of that external resistor. C is the capacitance of the capacitor. Time constant is for a capacitor resistor circuit the product of the capacitance and the resistance, giving a measure of the rate of charging and discharging the capacitor. Symbol tau, this. Sometimes capital T is used instead, because if you look at the Greek alphabet, you have capital tau and simple tau, and capital tau looks like a capital T. Alright, so that I think is the end of this lesson. We have gone through all these slides here, but let's have a look at your book also. So we went through all this. The graphs are there. Okay, so I think that's the end of that part. And the capacitor mathematics, I have a separate lesson on the logarithms for this, but also we can go through this briefly over here. So I have explained all this. Remember, we went through these examples. Okay, make sure you answer all these questions. You should study the definitions, charging, and then we have here also answer all these questions. Okay, check the answers after you do. Okay, so let's briefly also go through this here. Okay, let's go through some examples. That's better. We are using those equations. Okay, the equations that I showed you over here for capacitor discharging and for capacitors charging. Okay, so these equations. Now if you look at your textbook directly, they have not given you these equations for capacitors charging, but I derived them, so then it will be easier for you. Okay, and also maybe if you look at your past exam papers, in the last few pages, data, formula and relationship sheet, you might get some of these equations there as well. Okay, now we are in the last part, chapter 7.2.3. let's go through some examples. A 0.03 farad capacitor is fully charged by a 12 volt supply and then connected to discharge through a 900 ohm resistor. How much charge remains on the capacitor after 20 seconds? So they have given us the time t, they have given us the capacitance, they have given us the V0, the initial charge, and the R, you see. So therefore we are going to use one of these equations which has the relevant quantities. So they are asking how much charge, so that means we have to find Q. So let's use this equation. Q is equal to Q naught e to the power minus T over RC. So Q naught is 0.36. How did we get that? From Q is equal to CV. Now Q naught is equal to C V naught. V naught is the initial potential difference across the capacitor, that is when it is fully charged, so that is 12 volts. Okay, so instead of writing it like this, they should have written Q naught is equal to C V naught. Now C is a constant for the capacitor, so C also they have given 0.03 farads. Substitute, then you get this. Okay, now we can use this here. Q is equal to Q naught e to the power minus T over RC. Q naught is 0.36 coulombs, then T they have given. So remember, I told you when we have these equations, for a particular time t, for a certain time t, we can find what is the charge on the capacitor, what is the potential difference across the capacitor, and what is the current through the capacitor, using these equations when the capacitor is discharging, not when it is charging, when it is discharging. So remember which equations you are supposed to use when the capacitor is charging, and which equations you are supposed to use when the capacitor is discharging. See, here it's discharging. So let's see. Now very easy. 0.36 e to the power minus T is 20 over RC. R is 900. C C is 0.03. So we have this. Okay, so when the time is 20 seconds, the charge on the capacitor which is discharging is 0.17 coulomb. So you see, very easy. So here we have this is, remember, exponential curve, exponential decay curve, and then exponential. Yeah, we had the two types of curves you saw. Okay, now this one, a 0.03 farad capacitor is fully charged by a 12 volt supply and is then connected to discharge through a 900 ohm resistor. What is the potential difference of the capacitor after 20 seconds? So again, very simple. Now here they are asking you the potential difference. So based on that, you know that you are supposed to use this equation. So that's what they are doing. Initial potential difference, that is when the capacitor is fully charged, is 12, and remember this is for capacitor discharging. So that's why we are using this equation when the time is 20 seconds. RC, T over RC, R is 900, C is 0.03. So we get this, very simple. And now let's do a question on the current when the time is 20 seconds. So you see, in all these cases the time is 20 seconds and it's for the same capacitor. So now let's find the current when the capacitor is discharging when at the time 20 seconds. So for this, again, we need I naught, and I showed you how to find I naught. Remember when I was explaining these diagrams, I showed you how to find I naught. Okay, so it's also here. I should have actually made this V naught and this I naught here. Okay, R is constant. So okay, so let's see. So I naught is equal to V naught over R naught. Then V naught is 12, the initial potential difference. R is 900. So you get the initial current. This is when the capacitor is going to discharge when the time is 0 seconds. Okay, as soon as you connect it. So we have this. Then very easy. T is again 20. R is 900, C is 0.03, and you get 6.4 milliampere. So you can practice these questions. Okay, so this actually is the mathematics involved in this. Those who are taking A-level mathematics will be very familiar with this, but in your case the equations are there, and also you can go through the logarithm lessons to understand this better. Okay, so make sure you answer all these questions. And here they have told you what an exponential curve. Exponential curves are mathematical functions generated by each value being proportional to the value of one variable as the index of a fixed base. Index means the power. Okay, so b to the power of x. One variable as the index of a fixed base is b. Fixed base, see, it's the fixed base. X is the power. This is the last part. Make sure also after you finish answering all those questions and checking the answers to do this end of chapter questions as well. After that you can do the questions on from the revision guide, which is based on capacitors. The next lesson is electromagnetic effects.